Hey, 12th graders. So we are on our last lesson of this unit. My hope is to finish this lesson in this one video, and then for us to have some follow through practice days before we go into review and then take the test. So just keep that in mind that this is the last time we're going to learn something new. And then moving on, we're going to have one more video lesson about just practicing all of this because these are all brand new concepts. And so we're still just getting used to it. So what we've talked about so far is what a limit is and how we find the slope of the tangent line. In other words, your instantaneous rate of change. And then we learned that that really can change no matter, depending on where you are on a certain curve. Unless you're a line, then your slope is always the same, a straight line, right? And then we learned about so that was what a derivative is that it gives us a function to tell us what the slope of the tangent line would be depending on where we are in the curve. And now we're finally going to learn how to actually find the derivative of a certain type of function. So we're going to find derivatives of polynomial functions, which are all of these guys where they have some sort of exponent situation going on. So you can see that in your notes that they all have some sort of exponent idea. This is not the only way to find derivatives, but this is the only way you guys will be held responsible in the exam to find derivatives and in this class in order to find derivatives. So this is the only strategy you will have. There are lots of other strategies out there. You find derivatives of trigonometric functions, you find derivatives of logarithmic functions, of exponential functions. There's a lot of different ways to find it. We're just not going to learn it in this class. So what we are going to do first is that we're going to learn that our calculator can help us in terms of visualizing what the derivative is. So if you have a TI-84, this part of the video tutorial, all I'm doing is talking about TI Nspires, but go ahead and click on the link that I'm going to provide right here, and you can mute this and let this play until we're moving on, and click on this link, and that link will take you to 84 instructions. TI Nspires. What we want to do is, that changed the brightness a lot, sorry. What we want to do is we want to first graph our original function. So I just double click on this white space here and I graph 5x. Now it is a line, right? And we know that the derivative of a line is really just its slope, right? Because no matter what, your tangent line will just be the actual line. And so we could just automatically right now know that, like, no matter what, the derivative of this function is just the slope of this function. And the slope of this function is 5. So what I want to do, though, is show you how we could graph it. If I double click, now we're at F2, right? So above is F1, below is F2. If you click right here on this button, it gives you a whole list. I'm so sorry that's really hard to read, but it gives you a whole list of options. Right here is a derivative option, and I want you to click on that option right there. And now you can notice that we're starting to see something that seems familiar, which is the notation for derivatives, where it's dy dx. But what we're going to do, instead of dy, we need to put x down here. So notice we're looking for an input. I'm going to put x and then scroll over. And then just notice that dy over dx, if we think about it mathematically, is the same as d over dx times y. Right? We could think of it as over 1, and if we wanted to multiply it together, those would come together like that. So in this situation, what we're doing is we're actually saying dy dx, and instead of y, we want to reference, we want to reference our f1 function. We want to reference the function that we just graphed, this line right here. So I'm going to do it again because I lost it. Grab it, dy dx, and instead of y, I'm going to do f1 of x, which was the guy that was above. Notice that this is f2, the guy that we just graphed. This line, this blue line, is f1 of x. I'm literally going to go down to my touchpad, find f, which is next to g, type f, and then 1, and it automatically is like, oh, that's something that's special in this circumstance, which it is. It's the thing that we just graphed. And then I'm just going to do parentheses x, and then press enter. We don't see anything at first because my Zoom is crazy. You might see it because your Zoom hopefully isn't crazy, but I am going to zoom out. We know that the slope is 5, and so it makes sense that then the derivative would just be y equals 5, which is the slope. And we can see that graphed here. So your graphing calculator does graph the derivative function on your graphing calculator with the original function, the derivative with the original. It doesn't tell you what the equation is, but if you know that this is something that's available to you and you don't remember how to find the derivative on a test, you could always graph the derivative using your graphing calculator, and then from there you can try and piece together what the equation would be, which is what we're going to do for the rest of this example. So for this one, we know that the derivative is just the slope of a line. If we're just talking about a line, like 5x is a line, whereas this would be a curve. So we know that the derivative is just y equals 5. So y prime equals 5. It's just the slope of our original function. E basta. Okay, so let's try it again. Hopefully TI-84 is your back, and you can follow along. I'm just scrolling up and then deleting all the things. Here I'm going to put x squared, and I would like for you to also now graph the derivative of that function. So we're going to go to our little guy next to the book here, click on the derivative. We're going to do x down here to the side. We're going to call it f1 of x and press enter. So this is a line. The derivative function of this quadratic is a line, and that's true of all quadratics. The derivative of every quadratic is a line. We see that it goes through the origin, which is pretty cool, and all we want to know now is what the slope would be if we're talking about y equals mx plus b, trying to create what this derivative function would be. So I just want to go ahead and hit trace on that derivative function. Notice it's a blue cursor, blue text. That means I'm on my original. So if I scroll up or down, doesn't matter. It changes. I just scrolled down and it changed to red, which means if I start scrolling around, it's going to talk to me about the red line. So I'm going to hit 1, enter, and it's going to give me a point. So I know that I go through the origin, and I know that I also have the point 1, 2. And I know that this is a line, so I could really quickly just write the equation of the line in this situation. Y minus 0 equals, oh wait, no, first I have to find the slope. M equals 2 minus 0 over 1 minus 0, which is a slope of 2. So I know that I have a slope of 2, and I know that I go through the origin, so I could do y minus 0 equals 2 times x minus 0, or hopefully we've pieced together at this point that your equation is y equals 2x, y prime. The derivative of this original function is 2x, the equation of a line. Okay, let's do it again. I think I'm going to try this. I think if I double click on here, I don't need to change this because I would have to retype it every time, but it's going to stay the same. I'm still referring to the equation that's up above. So I'm going to try out just not rewriting the derivative function and instead rewriting the placement function, which will be 3x squared, enter. Awesome. So my placement function has changed. My derivative function has changed with it. So 3x squared, just a little bit skinnier of a quadratic, but the equation of the derivative is still a line. And so it still goes through the origin here. So that's 1 point. And that would also be our y-intercept if we're trying to think about y equals mx plus b. And then if I hit trace, I can go ahead and find another point, which, hey, it did for me. 1, 6 is a nice point that we can use. So 1, 6 means that I have a slope of 6, right? I would go up 6 over 1. So I know that my slope is 6. So I know that since I go through the origin, mx plus b, 6x plus 0 would just be y equals 6x. Y prime, because we're talking about the derivative. So what we're doing here is we're grabbing a whole bunch of examples of original functions and what their derivative functions look like. And I want you to try and just pause for a second and see if you notice any behaviors between like these relationships between these two, because there is an actual like formula that we go through in order to find these guys. So just pause, and I want you to go ahead and tell me, do you have a hypothesis about what this situation is and what this relationship is? Okay, so now we're going to move on and talk about cubic functions and look at what happens to the derivative when we talk about it in a cubic way. Sorry. There we go. Again, I'm going to not change my second. I'm just going to go up here and change my first, which is just x cubed.